Welcome. Today, we're diving deep into the heart of your automatic transmission, the valve body. This critical component is often called the brain of the transmission system. Think of the valve body as the transmission's brain, a complex control center that makes intelligent decisions about gear changes based on driving conditions. Here we see a directional control valve, one of the key components in hydraulic systems. Notice the two solenoids labeled A and B, along with pump and tank connections that manage fluid flow. The valve body manages the flow of hydraulic fluid throughout the transmission. It receives pressurized fluid from the pump and directs it precisely to engage the appropriate gears. This cutaway diagram reveals the incredible complexity inside a hydraulic valve. You can see the intricate network of internal pathways, ports, and precision-engineered components that work together. Unfortunately, transmission valve bodies are failing more frequently today than in the past. This is due to increased complexity in modern transmissions, more electronic components, contamination issues, and higher operating stresses. In this comprehensive series, we'll explore exactly how valve bodies work, why they're failing, and what symptoms to watch for. Understanding these systems will help you maintain your transmission and avoid costly repairs. The valve body functions as a sophisticated maze of channels and passages, precisely controlling the flow of transmission fluid throughout the system. This cross-sectional view reveals the intricate network of internal passages and channels that make up the valve body's core structure. These channels form an interconnected network that allows transmission fluid to flow to specific destinations within the transmission system. Transmission fluid flows through these channels in a precisely controlled manner, reaching clutch packs and band servos at exactly the right pressure and timing. The valve body's internal components work together with extreme precision. Each channel must be manufactured to exact specifications to ensure proper fluid pressure and timing for smooth gear transitions. This intricate hydraulic routing system enables the transmission to respond instantly to driving conditions, directing fluid exactly where it's needed for optimal gear engagement and vehicle performance. The valve body's primary function is controlling gear shifting through precise hydraulic fluid management. When you accelerate or decelerate, the valve body determines which gears to engage for optimal power delivery. Inside the valve body, hydraulic fluid flows through precisely engineered channels and passages. This pressurized fluid acts as the power source that activates clutch packs and band servos throughout the transmission. When shifting into first gear, the valve body directs hydraulic pressure to engage specific clutch packs. Watch as pressurized fluid flows from the valve body to activate the appropriate components. For a smooth shift to second gear, the valve body redirects hydraulic pressure. It simultaneously disengages the first gear clutch pack while engaging the second gear components, ensuring seamless power transfer. This hydraulic control system becomes more complex in modern transmissions. Here's a detailed schematic showing the intricate network of valves, solenoids, and fluid passages that work together. The valve body optimizes power delivery and fuel efficiency by selecting the appropriate gear ratio for each driving scenario. Whether accelerating from a stop or cruising at highway speeds, it ensures smooth transitions that maximize both performance and economy. Transmission valve bodies come in two main types: hydraulic and electronic systems. Each type operates on fundamentally different principles to control gear shifting. Older vehicles use purely hydraulic valve bodies that operate mechanically. In these systems, throttle valve pressure works against governor pressure to control shift valve movement. Throttle pressure increases with engine load, while governor pressure increases with vehicle speed. These opposing forces determine when the shift valve moves to change gears. Modern vehicles use electronic valve bodies with computer-controlled solenoids. The engine control unit receives data from various sensors and precisely controls solenoid operation. The computer sends precise electrical signals to the solenoids, which then control hydraulic fluid flow with much greater accuracy than purely mechanical systems. The key differences between these systems are clear. Hydraulic systems rely on mechanical pressure balance, while electronic systems use computer control for more precise fluid direction and improved shifting performance. Solenoids are the electrohydraulic switches that serve as the control interface between the transmission's electronic brain and its hydraulic systems. A solenoid consists of an electromagnetic coil that, when energized, moves a plunger to control the flow of transmission fluid through specific passages. Solenoids manage three critical functions in automatic transmissions. Let's examine each of these essential control operations. First, solenoids control torque converter lockup, determining when the converter mechanically connects for maximum fuel efficiency. Second, they regulate transmission pressure, ensuring the hydraulic system maintains optimal pressure for smooth operation. Third, and most importantly, solenoids control gear shifting by directing transmission fluid to the appropriate clutch packs and bands. Modern transmissions require significantly more solenoids than their predecessors due to increased complexity and precision requirements. This valve body contains multiple solenoids, each labeled with specific designations. Modern transmissions may have 8 or more solenoids compared to just 2 or 3 in older designs. The evolution from simple 2 or 3 solenoid systems in the 1990s to today's 8 to 12 solenoid configurations reflects the dramatic increase in transmission sophistication and the precise control required for modern fuel efficiency and performance standards. The manual valve serves as your direct connection to the transmission's hydraulic control system. When you move the gear shifter, you're physically controlling this critical valve component. The gear shifter in your vehicle is mechanically linked to the manual valve inside the transmission. This direct connection ensures that your gear selection immediately affects the valve's position. Inside the transmission, the manual valve is a precision-machined component that slides within the valve body. Different positions of this valve align with specific hydraulic passages. When you select drive, the manual valve moves to align with the drive passage. This allows hydraulic fluid to flow through the correct channel to engage the appropriate clutches and bands. Selecting reverse moves the manual valve to a different position, directing hydraulic fluid through the reverse passage instead. This precise control ensures only the correct gear engages. The manual valve represents your most direct control over the transmission. Unlike electronic controls that interpret signals, the manual valve provides immediate mechanical response to your gear selection, making it a critical component in transmission operation. Modern transmission valve bodies are failing more frequently than their predecessors, and the primary reason is dramatically increased complexity. Today's transmissions are engineering marvels, but this sophistication comes at a cost. The evolution of automatic transmissions tells the story clearly. In the 1980s, most vehicles had simple 3 or 4-speed transmissions. Today's vehicles commonly feature 8, 9, or even 10-speed transmissions. This dramatic increase in gear count requires exponentially more complex internal components. Let's examine what this means inside the transmission. Modern transmissions contain multiple planetary gear sets, numerous clutch assemblies, and complex brake systems. Each additional gear requires precise coordination between these components. The valve body must control all of these components with hydraulic precision. Here's what a modern valve body looks like when disassembled. A modern valve body contains over 50 individual valves, more than 100 springs and clips, dozens of fluid passages, and multiple electronic solenoids. Each component must work in perfect harmony. Beyond mechanical complexity, modern valve bodies rely heavily on electronic controls. Computer systems monitor dozens of sensors and make split-second decisions about gear changes. This complexity creates exponentially more potential failure points. Where older transmissions had perhaps 20 critical components, modern systems have hundreds. Each additional component represents another opportunity for malfunction. The increased complexity of modern transmissions, while providing better performance and fuel economy, has made valve bodies significantly more susceptible to failure. Understanding this complexity is crucial for proper maintenance and diagnosis. Contamination is one of the leading causes of valve body failure in modern transmissions. Understanding how contaminants accumulate and interfere with valve operation is crucial for maintaining transmission health. In a clean transmission, fluid flows smoothly through the valve body passages. The valves can move freely and precisely, allowing for proper hydraulic control and smooth gear shifts. However, over time, three main types of contaminants enter the transmission fluid. First, debris particles from worn components and external contamination create irregular solid particles that can block narrow passages. Second, sludge forms when transmission fluid breaks down due to heat and oxidation. This sticky, tar-like substance adheres to valve body surfaces and creates thick blockages in critical passages. Third, metal particles result from normal wear of transmission components like clutches, bands, and gears. These microscopic metal shavings accumulate in the valve body and interfere with precise valve movement. As these contaminants accumulate, they begin to clog the narrow passages within the valve body. Watch how blockages form and restrict fluid flow, preventing valves from moving smoothly and precisely. With passages blocked, valves can no longer move freely. This leads to delayed shifts, harsh engagement, and eventually complete valve body failure. The precise hydraulic control that modern transmissions depend on is compromised. This is why maintaining clean transmission fluid is absolutely critical. Regular fluid changes remove contaminants before they can accumulate and cause expensive valve body damage. Prevention through proper maintenance is always more cost-effective than repair. Transmission fluid degradation and overheating create a destructive cycle that significantly impacts valve body performance. Understanding this process is crucial for preventing costly transmission failures. Fresh transmission fluid is bright red and maintains excellent lubricating and cooling properties. Over time, heat, oxidation, and contamination cause the fluid to darken and lose these critical characteristics. As transmission fluid degrades, it loses its ability to lubricate moving parts and transfer heat effectively. This creates a dangerous cycle where poor cooling leads to overheating, which accelerates further fluid breakdown. This creates a destructive cycle. Overheating breaks down the fluid chemically, reducing its lubricating ability. Poor lubrication increases friction and heat generation, which further degrades the fluid and perpetuates the cycle. Degraded fluid and overheating directly damage valve body components. Seals and gaskets deteriorate, passages become clogged with debris, and solenoids fail due to contaminated fluid and excessive heat. Regular transmission fluid changes are the most effective prevention method. Fresh fluid maintains proper lubrication and cooling, breaking the degradation cycle and protecting valve body components from heat damage. Following manufacturer recommendations for fluid change intervals is essential. This simple maintenance step prevents the degradation cycle and extends valve body life significantly. Like any mechanical component in your vehicle, the transmission valve body experiences natural wear and tear over time. This deterioration is inevitable and occurs through normal operation. The valve body contains numerous precision-machined components that work together under high hydraulic pressure. Over thousands of miles of operation, these components gradually wear down at critical contact points. The wear process happens gradually over many thousands of miles. Initially, valve surfaces are smooth with precise tolerances. As mileage accumulates, surfaces begin to score and clearances increase. Several factors accelerate the wear process. Frequent use and high engine revolutions create constant stress on valve components. High hydraulic pressure cycles cause repeated loading and unloading of parts. Material fatigue also plays a significant role as springs weaken and metal components develop microscopic cracks. The most common wear areas include valve bores, governor plugs, pressure sleeves, and seal rings. Environmental factors like moisture and contaminants also contribute to wear through internal corrosion. This surface deterioration further accelerates the wear process and reduces component life. Ultimately, valve body wear and tear is an inevitable consequence of normal transmission operation. While regular maintenance can slow this process, eventual replacement becomes necessary as components reach the end of their service life. Not all valve body failures are caused by normal wear and tear or poor maintenance. Some transmissions have inherent design flaws that make them particularly susceptible to valve body problems from the very beginning. Design flaws are different from normal wear because they represent manufacturing defects or poor engineering decisions that cause problems, regardless of how well the transmission is maintained. The Nissan RE5 transmission is notorious for a specific design flaw. The radiator design allows engine coolant to leak into the transmission fluid, creating a contamination problem that directly affects the valve body. This diagram shows the complex internal structure of the RE5R05A transmission. The design flaw allows coolant to enter the system and flow directly to the valve body, where it mixes with transmission fluid and causes hydraulic control problems. This valve body diagram shows the intricate network of passages and control points. When coolant contaminates the transmission fluid, it clogs these precise hydraulic passages, damages seals, and ultimately leads to complete valve body failure. Other transmissions also have documented design flaws. Dodge 42RE, 47RE, and 48RE units suffer from faulty pressure solenoids and transducer problems. Some GM 8-speed transmissions experience shuttering issues related to valve body design. Understanding these known problems helps consumers make informed decisions and mechanics diagnose issues more quickly. Modern transmissions have evolved from simple on-off solenoids to sophisticated pulse-width modulated solenoids. Understanding this evolution helps explain why today's transmissions are both more precise and more prone to failure. Traditional solenoids operate like simple switches. They are either fully on or completely off. When energized, they create maximum magnetic force. When de-energized, they create no force at all. This diagram shows how traditional solenoids control valves. The coil is either energized, closing the valve completely, or de-energized, opening it fully. There are no intermediate positions. Pulse width modulation, or PWM, revolutionizes solenoid control by rapidly switching the solenoid on and off at high frequency. By varying the width of these pulses, engineers can achieve precise control over the average force output. PWM control requires sophisticated electronic circuits. This circuit uses a timer chip to generate precise pulse patterns. The duty cycle, the percentage of time the signal is high, determines the effective power delivered to the solenoid. The PWM signal creates a square wave pattern. When the duty cycle is 25%, the solenoid receives power only 1/4 of the time, resulting in 25% average force. At 75% duty cycle, it receives 3/4 power. Higher duty cycles provide proportionally more force. This variable control allows transmission engineers to fine-tune hydraulic pressure for smoother, more efficient gear changes. PWM solenoids offer significant advantages over traditional designs. They provide infinite variability between zero and maximum force, enabling precise pressure control that improves shift quality and fuel efficiency. Modern transmissions implement PWM control through sophisticated electronic circuits. This ground-controlled circuit shows how computer signals precisely modulate solenoid operation for optimal transmission performance. However, this sophistication comes at a cost. PWM solenoids require complex electronic control circuits, precise timing, and multiple sensors. Each additional component represents a potential failure point, making modern transmissions more prone to electronic malfunctions. While PWM solenoids deliver superior performance and control, their increased complexity explains why modern transmissions experience more frequent electronic failures compared to simpler hydraulic systems of the past. Delayed shifting is one of the most noticeable symptoms of valve body problems. When you move the gear shifter, there should be an immediate response from the transmission. Here we see a typical gear shifter in a vehicle. When the driver moves from park to drive or reverse, the transmission should engage almost instantly. In a healthy transmission, gear engagement happens within 1 to 3/10 of a second after moving the shifter. This creates a smooth, immediate response. However, when the valve body is failing, this delay can extend to 1 to 3 seconds, or even longer. You'll notice a distinct pause where nothing happens after moving the shifter. This delay occurs because the valve body is struggling to build sufficient hydraulic pressure to engage the clutch packs or bands needed for the selected gear. Inside the transmission, the valve body controls hydraulic fluid flow. When it's not functioning properly, pressure buildup becomes slow and inconsistent. Normal valve bodies maintain consistent hydraulic pressure, allowing immediate gear engagement. Failing valve bodies struggle to build this pressure quickly. This delayed shifting is most noticeable when moving from park to drive or reverse, as these require the most significant hydraulic pressure changes to engage the transmission properly. If you experience these delays consistently, especially during cold starts or after the vehicle has been sitting, it's a strong indicator that your valve body needs professional attention. Incorrect and erratic shifting occurs when the transmission's valve body makes poor decisions about when and how to change gears. Instead of smooth, predictable shifts, the transmission behaves unpredictably. Let's compare normal shifting patterns with erratic ones. In normal operation, the transmission shifts smoothly from first gear to second, then third, then fourth in a predictable sequence. However, when the valve body malfunctions, you get erratic shifting. The transmission might jump from first gear directly to third, then back down to second, creating a chaotic and unpredictable pattern. This diagram shows how modern, adaptive shift systems are designed to prevent incorrect shifting by monitoring vehicle speed and selecting appropriate gears for different driving conditions. When the valve body fails, it essentially makes wrong decisions about gear selection. Think of it as the brain of the transmission becoming confused and sending incorrect signals. But when contamination, wear, or electronic failures occur, the valve body starts making incorrect decisions, leading to the erratic shifting patterns that drivers experience. The key symptoms of incorrect and erratic shifting include unexpected gear changes, shifting at inappropriate speeds, and unpredictable transmission behavior that makes driving uncomfortable and potentially unsafe. Shift flares are a critical symptom of valve body problems that drivers often notice as unusual engine behavior during gear changes. During a normal upshift, the engine RPM should decrease smoothly as the transmission engages the next higher gear. The RPM gauge shows this as a clean drop in engine speed. Here we see a normal upshift pattern. The RPM rises during acceleration, then drops cleanly as the next gear engages. This indicates proper valve body operation and gear engagement. A shift flare occurs when the engine RPM increases significantly during the upshift instead of dropping. This creates a noticeable spike in engine speed before the gear finally engages. Shift flares occur when the valve body fails to maintain proper hydraulic pressure during gear changes. Insufficient pressure prevents the clutch packs from engaging firmly, causing the transmission to slip. When the valve body cannot provide adequate hydraulic pressure, the clutch packs fail to engage properly. This allows the engine to rev freely while the transmission slips, creating the characteristic shift flare. This condition indicates that the valve body is not functioning correctly and requires immediate attention to prevent further transmission damage and ensure safe vehicle operation. The torque converter clutch is a critical component that can cause significant drivability issues when it malfunctions. These problems are directly controlled by the valve body and can create symptoms that drivers often mistake for engine problems. The torque converter contains a lock-up clutch that mechanically connects the engine to the transmission when engaged. This clutch is controlled by hydraulic pressure from the valve body. When the valve body sends hydraulic pressure to engage the torque converter clutch, it should create a smooth, solid connection. However, when problems occur, the results are immediately noticeable to the driver. The most common symptom of torque converter clutch problems is shuddering. This feels like the entire vehicle is shaking or vibrating, typically occurring during acceleration or when cruising at highway speeds. Another serious symptom is stalling. When the torque converter clutch fails to disengage properly, it can cause the engine to stall when coming to a stop or during low-speed driving situations. These torque converter clutch symptoms often feel exactly like engine misfires or rough running conditions. This similarity can mislead both drivers and technicians into diagnosing engine problems when the real issue lies within the transmission valve body. The valve body controls the hydraulic pressure that engages and disengages the torque converter clutch. When the valve body malfunctions, it can send incorrect pressure signals, causing inconsistent clutch engagement, slippage, or binding that creates these troublesome symptoms. Getting stuck in gear represents one of the most severe symptoms of valve body failure. When this occurs, the vehicle becomes completely stuck in either neutral or a single gear, making normal driving impossible. Normally, a transmission can smoothly shift between all gear positions. The driver can select park, reverse, neutral, drive, and various manual gear positions as needed. In normal operation, when the driver selects drive, the transmission responds by engaging the appropriate gear and allowing smooth shifting between forward gears. However, when the valve body fails severely, the transmission may become stuck in neutral. No matter what gear the driver selects, the vehicle remains in neutral and cannot move forward or backward. This severe malfunction is directly linked to the valve body, which controls all hydraulic fluid routing in the transmission. When the valve body fails catastrophically, it can no longer direct fluid to engage any gears. The valve body contains numerous channels, passages, and solenoids that must work together to engage gears. When these components fail or become blocked, the transmission loses its ability to shift into any gear. The internal complexity of modern transmissions means that when the valve body fails, it affects the entire system. Multiple gear sets, clutches, and bands all depend on precise hydraulic control from the valve body. Getting stuck in gear is considered a major malfunction because it renders the vehicle inoperable. This symptom typically requires immediate professional attention and often indicates that valve body replacement or major transmission repair is necessary. Unusual knocking noises during gear changes are a serious warning sign of mechanical problems within the transmission valve body. These sounds indicate internal components are not functioning properly. The valve body contains numerous moving parts, including valves, springs, and hydraulic passages. When these components wear or become damaged, they can create knocking sounds during operation. These knocking sounds are most noticeable during gear changes, especially when shifting from park to drive, or when the transmission is under load during acceleration or braking. Knocking noises typically occur in three main scenarios. First, during gear changes when the transmission shifts between park, reverse, neutral, and drive positions. Second, at low speeds, particularly during city driving under 25 miles per hour when the transmission is frequently shifting between lower gears. Third, during braking when the transmission downshifts to help slow the vehicle, putting additional stress on the valve body components. The mechanical causes of knocking include worn valves that no longer fit tightly in their bores, creating a loose rattling sound when hydraulic pressure moves them. Damaged or broken springs within the valve body can also cause knocking as they fail to properly control valve movement, leading to vibration and noise. Metal debris from worn transmission components can accumulate in the valve body, creating knocking sounds as particles interfere with smooth valve operation. These knocking noises should never be ignored as they indicate mechanical damage within the valve body. Continued operation can lead to complete valve body failure, extensive transmission damage, and costly repairs, or complete transmission replacement. If you hear unusual knocking sounds during gear changes, especially at low speeds or when braking, have your transmission inspected immediately by a qualified technician to prevent further damage. When a solenoid within the transmission valve body malfunctions, it can trigger your vehicle's check engine light. Understanding this connection is crucial for proper diagnosis. Under normal operation, the solenoid receives proper electrical signals from the transmission control module. The electromagnetic coil energizes correctly, moving the plunger to control hydraulic fluid flow. When a solenoid malfunctions, it may fail to receive proper electrical signals, experience internal component failure, or become stuck due to contamination. This disrupts normal transmission operation. The transmission control module continuously monitors solenoid performance. When it detects a malfunction, it immediately sends a signal to the engine control unit. This triggers the check engine light on your dashboard. The illuminated warning light alerts you that the vehicle's computer has detected a problem that requires attention. However, the check engine light can indicate many different issues throughout the vehicle, not just transmission problems. This is why proper diagnosis is essential. To determine the root cause, Technicians use an OBD scanner to read diagnostic trouble codes. These codes provide specific information about which solenoid has failed and the nature of the problem. Common transmission-related codes include P0750 for shift solenoid A malfunction, P0755 for shift solenoid B, and P760 for shift solenoid C. Each code points to a specific component within the valve body. Understanding the internal structure of solenoids helps technicians pinpoint exactly which component has failed and plan the appropriate repair strategy. Remember, while a check engine light can indicate transmission valve body issues, proper diagnostic code reading is essential to confirm the specific problem and avoid unnecessary repairs. Difficulty downshifting is a common symptom that indicates problems with hydraulic fluid flow within the transmission valve body. When the transmission struggles to shift to a lower gear, it signals potential trouble in the hydraulic control system. Downshifting occurs when the transmission needs to change from a higher gear to a lower gear, such as when slowing down or needing more power for acceleration. This process requires precise hydraulic control. When downshifting becomes difficult, the transmission may hesitate, delay, or fail to engage the lower gear smoothly. This creates a noticeable problem for the driver. The valve body contains a complex network of hydraulic passages, valves, and solenoids that control fluid flow to different clutch packs. Each gear change requires specific hydraulic pressure patterns. For successful downshifting, hydraulic fluid must flow through specific passages to release the current gear's clutch pack and engage the target gear's clutch pack simultaneously. Problems with downshifting typically occur when hydraulic passages become blocked or restricted. This prevents proper fluid flow to the clutch packs that control gear engagement. When passages become blocked by debris, worn valve components, or contaminated fluid, the hydraulic pressure cannot reach the appropriate clutch packs, causing downshift difficulties. Drivers experiencing downshift problems will notice several symptoms. These include delayed gear engagement, hesitation during the downshift process, engine revving without proper gear change, and poor acceleration response when more power is needed. These downshift difficulties indicate that the valve body's hydraulic control system requires attention. Proper diagnosis and repair of the valve body can restore smooth downshifting operation and prevent further transmission damage. The automotive industry has seen significant growth in the remanufactured valve body market. These components offer a practical solution for transmission repairs, combining cost savings with reliable performance. Remanufactured valve bodies typically cost 50 to 60% less than new components. While a new valve body ranges from $800 to $1,200, remanufactured units cost between $400 and $600, making them an attractive option for budget-conscious repairs. The remanufacturing process involves 5 critical steps. First, complete disassembly and thorough inspection of all components. Second, precision cleaning and machining of valve body castings. Third, replacement of all worn seals, gaskets, and internal components. Fourth, careful reassembly followed by comprehensive testing. Finally, quality certification to ensure performance standards. Remanufactured valve bodies meet strict quality standards. They comply with original equipment manufacturer specifications and undergo comprehensive hydraulic pressure testing. Electronic functions are verified, and most come with warranty coverage. Industry data shows remanufactured valve bodies achieve 98% reliability rates, matching new component performance. Remanufacturing provides significant environmental benefits. It reduces manufacturing waste by reusing existing components and conserves raw materials that would otherwise be needed for new production. The process has a 75% lower carbon footprint compared to manufacturing new parts, while extending the life cycle of automotive components and supporting sustainable repair practices. The remanufactured valve body market has experienced remarkable growth, with 35% annual increases over recent years. This growth reflects increasing acceptance by repair shops and vehicle owners who recognize the value proposition. As transmission complexity increases and new part costs rise, remanufactured components provide an essential alternative for maintaining vehicle fleets and extending transmission service life. Proper maintenance is the key to preventing valve body failures and ensuring your transmission operates smoothly for years to come. Regular care can save you thousands of dollars in major repairs. Regular transmission fluid changes are absolutely crucial for valve body health. Clean fluid prevents contamination, maintains proper lubrication, and keeps operating temperatures within safe limits. The cost difference between regular maintenance and major repairs is dramatic. Spending a few $100s on maintenance can prevent thousands in valve body replacement costs. Early detection of valve body issues is equally important. By recognizing symptoms like harsh shifting or delayed engagement, you can address problems before they cause catastrophic transmission failure. Understanding how valve bodies work and what can go wrong empowers you to take better care of your transmission. Knowledge combined with proper maintenance is your best defense against costly repairs. By following these maintenance principles and staying alert to warning signs, you can ensure your transmission valve body continues to operate efficiently, saving you money and keeping you on the road.